Hello everyone, welcome back to another Python video. In this video, we're going to be doing another object-oriented programming case study where we're going to try to represent a 2D vector from mathematics by using classes, attributes, and methods, and so on by following the principles of object-oriented programming. So here we go. When we think about a vector, we're going to have two attributes, x and y coordinates. Basically, a vector is like a point, often it has direction, but in this case, we're just going to call it a vector, and it's going to have the two attributes of x and y. And to get this started is fairly simple. We can just say self, and when we initialize, we're going to say that we're going to require the two values representing x and y. And then we're going to go self, we'll make them private variables, so we'll do self dot underscore x is equal to x, and self dot y is equal to y, and that is our vector with the x coordinate, y coordinates for this object. And then since we have these private variables, let's write some getters. We're going to say property. It's going to be the x getter, and we're going to say def x self. We're going to return self dot underscore x, and we're going to do the same thing for y. So let's copy that over, and then we're going to have y, and we're going to be able to return y. And since we have our object made, our class initialized and set up, we're gonna make it representable and printable. So let's do def. Let's do a string of equivalent override here. So this is a base override. And then what we're gonna say is how should we represent this? We're gonna say return a vector at x self.x comma self.y in that format. So we're going to write f. We're going to do a formatted string, and this is going to be trapped inside a curly brace like so. Curly brace like so. And then for our representation override, we're going to make it return the same thing as a string. So we're going to say return self dot string. So just having these here, we have a y getter, an x getter, so we should be able to access our x coordinate and y coordinate as read-only values. And here, this just allows us to interact and print our object like so. So if we go down, if we were to say that our vector 1 is a vector 1, 2, we can do print v1 to execute our code. And we will get this type of message, and we're allowed to now put inside a list to have like lists of vectors if we wanted to, thanks to the representation method. So we have now initialized a really good starting point for our class called vector. All right, so now we're going to do vector addition. When we add two vectors, let's say p and q, we're going to add their x components and y components together, and it's going to generate a new vector called that. So to make our life easier, what we can do is say that we're going to override the base function called add. This allows vector plus vector behavior. So we can say that it's going to return a new vector object that we have initialized. So we're returning a new one where we're going to say that when given in another vector, we're going to take self.x plus other vector x, and this is possible because of our property getters, and the y value is going to be self.y plus self the other vectors y. So in this situation here, we can say that self is left operand of the plus operator, and we can say that the other vector is the right operand of the plus operator. So that's going to allow us to have that kind of behavior coded. So let's test that function. So we're going to have v2 vector is going to be at a location of 5, 10. These are our two vectors being printed, and then we can say that v3 is going to be returning the result of v1 plus v2 right there, and print v3 like so. And we get 6 and 12, where we added the 1 and the 5, the x components. We got 6 and 2 and the 10 to have the y values, y coordinate be 12 for our vector called vector v3. Perfect. And that helps us return a vector object that we are now defining. Now we're going to do a scalar multiple, right? So we're going to have this base function overrided. This is the base override of the operator. And what we're going to do is we're going to say that, well, this is going to be scalar. We're going to take a scalar value and multiply each components that we have. So we're going to say return. It's going to return a new vector. And we're going to say that we're going to take the scalar value and multiply it by self.x, comma. I'm going to take the scalar value and do self.y. And this is going to generate a new vector. So in this scenario here, if we were to go v4, say that we're going to do v1 times 3. Let's say we should be expecting 3, 6. So let's do v4. And we're going to get 3, 6. This got multiplied by 3 and this got multiplied by 6. And this is helping us do a base override so that we can have scalar multiplication that exists in mathematical vectors. Awesome. Then we're going to do dot product, which returns a scalar value. You're returning to, you're multiplying two vectors together, and it's going to be following this behavior. Okay, so we'll call this a dot product. And it's going to be self, and we're going to take other vector. Now, this is not going to have a base override. We're just going to say that this is a built-in method for any vector objects that we have. And then it's going to generate a new value. So what we're going to do is say that we're going to return self.x multiplied by the other vectors x. And we're going to add that with self.y multiplied by the other vector y. And then we'll just put that within parentheses so that we are enforcing BEDMAS here. Okay, and this is going to return an integer. So we have these two vectors here, v1 and v2. So if we want to say the dot product, we'll call it VP is equal to the v1 dot product. This is a method that we have created a name for. We didn't do any base override, so we can't use any built-in Python operators for this. And we're going to provide v2 and print dp value like that. And it's going to give us 25, which makes sense because we're going to do 1 times 5, that's 5. And 2 times 10 is 20, so we're going to get this value of 25. Okay. And then we're going to have this orthogonal check, which turns a Boolean. It's true if the two vectors are orthogonal to each other. If we had these two vectors and P and Q are orthogonal if the dot product equals 0. So we can say we're going to have a is orthogonal. Okay. Self with other vector. And what we're going to do is run our self dot product onto this. So we're going to say result. We can just do return self dot product with the other vector. And that's going to be, if that is equivalent to 0, we're going to return true. That means those two, our self and the other vector are orthogonal to each other. If not, it's going to be false. Okay. So we can also now check, we're going to have an ortho variable that says is v1 or is orthogonal to v2, and print ortho. It should return false because they're not, like that. Perfect. Okay, and then what we are going to do is scalar distance. We're going to take two vectors and we're going to get a scalar distance, like how far away each values are. And this is why at the very top we have imported square root, because our formula for the distance from one point to another requires a square root. Okay, so therefore we're going to get distance. We're going to have self, another vector. Okay. And we're going to be returning the square root of all this added up. So we're going to have the difference of x component and the y component all squared. So first we're going to do self.x subtracted by the other vector's x value, and we want to square all that. So we're going to do star 2. That, and then we're going to be adding that to self.y minus other vectors y. The order here really doesn't matter. And we're going to trap that in the bracket. This star 2, so that is squared, and now we have to apply square root on the entirety of the addition there, like so. Perfect. And then that's going to help us do distance. So let's say we have these two on v1, v2. We can say print distance from v1 to v2 is v1 distance, v2, like that. So we're going to have from these, we're going to have that units as 8.9. There's a scalar distance of 8.9 units from our vector 1, 2 to vector 5, 10. All right, and then we can now look at, we can calculate the magnitude of a vector by returning a scalar number. So if p is x1, y1, then the magnitude of vector p is the scalar distance from the origin. So we can just use this assistant formula where we make the other vector as it's just 0, 0. So we can say def magnitude of self is just returning a square, returning the self.distance from itself to this vector point of 0, 0, like that. And that's going to be the origin. Okay, so print f here, we can say that the magnitude of v1, let's do v2, is v2 magnitude. That. And it's going to be 11.18, like so. So we have vector 1 printed. Here we can say f v1 dot product v2. Put those in curly braces. Is that and their quotation mark here, and we're going to see is v1 orthogonal to v2 . We're just having some nicer output here. We're going to do v1 plus v2 equals v3, and then we can now do v1 multiplied by 3 is equal to v4, like that. Let's run our code. So in this scenario here, we have printed our vector 1, 2, 5, 10 to check if our string representations are working, which we wrote that code right here. Next, we have our distance formulas being calculated. So we have, we're running a distance from v1 dot to v2, because these are custom methods that we've created. We must use the dot and distance requires a parameter. So we're going to provide that parameter. Magnitude doesn't, because we're calculating the distance from itself to the vector, the origin of vector 0, 0. So we just run it like so. And then for dot product here, we're running a dot product from v1 to v2 of these two, and it's going to give us a scalar value of 25. We can check orthogonality, so this is false. We can add two vectors here. We're doing vector additions when we are adding x components to y components, so we get 6, 12. And we can do a scalar multiple of a vector as well, which stretches to vector of 3 and 6. So this is how we can use object-oriented programming, where we can now create our custom class that represents 2D vectors in a world of mathematics and linear algebra. And as always, thank you for watching and stay classy.